We have another problem here. Water flows through the pipes shown in the figure. The water's speed through the lower pipe is 5 meters per second, and a pressure gauge reads 75 kilopascals. What is the reading of the pressure gauge on the upper pipe? All right, so we do want to go ahead and just reference point 1, which they have in the picture, versus point 2. We know the pressure, the gauge pressure down here is 75 kilopascals. In this particular case, they've given us the speed. So the speed of the fluid down here is 5 meters per second. We're looking for this gauge pressure up here, so point 2. It doesn't tell us what the speed is. We do know that this second part of the pipe is 2 meters higher than the top pipe, and they're measuring center to center. So to find a pressure when we're dealing with fluids flowing, moving through a pipe, we need to use Bernoulli's equation. So P1 plus 1/2 rho V1 squared plus rho GY1. All of this stuff has to be constant, meaning it needs to equal all of these things, these terms added together at point 2 in the pipe. That's what we mean by the pressure plus 1/2 rho V squared plus rho GY being constant. This is our conservation of energy equation. It's in terms of pressure, but it's representing conservation of energy. So if we go ahead and just say Y1, that lower point is 0, then Y2 is the 2 meters. The fluid is flowing at both points 1 and 2. It should be flowing faster at point 2, simply because the pipe has narrowed down. So we're looking for gauge pressure at point 2. If you watch the previous example, you know we can make P1 and P2 both gauge pressures, and that's perfectly valid. So our gauge pressure 2 will equal 1/2 rho V2 squared minus 1/2 rho V1 squared plus rho GY2. I can factor out the 1/2 in the row. This time we have the rho GY term because there is a change in height. We know V1, we know Y2, we know this is water. So, oh, I forgot my P1, I'm sorry. Oh, minus. I forgot to bring pressure gauge 1 over. Oh my goodness. I pretend I know how to do math. I like to prove that I am as prone to mistakes as anyone, though I don't purposefully make my mistakes. I need to bring everything to the left if I'm solving for pressure gauge 2. Sorry about that. So pressure gauge 1 plus 1/2 rho V1 squared, that's already on the left. Bringing the other terms over, that's looking better. So pressure gauge 2 will be pressure gauge 1 plus 1/2 rho V1 squared minus V2 squared minus rho GY2. There we go. We know the pressure gauge 1, so we know this, we know the density, we know V1, we know all of this. We need V2, though, in order to solve for pressure in gauge 2. Okay. To relate and find speeds, we always use the continuity equation. where Q is equal to volume per time, or cross-sectional area times speed, where this is a constant. What that means, since I have dimensions, they give me the diameter at point 1 and the diameter at point 2 in the picture. So 6 centimeters is the diameter at point 1, 4 centimeters is the diameter at point 2. This time they've given me a speed. So what I'm going to do is I'm going to say A1 times V1. So the cross-sectional area of the pipe at point 1 times how fast that fluid is flowing at point 1. When we say it's constant, we mean it has to equal A2 V2. So V2, area 1 is going to be pi R1 squared. When I divide by area 2, that's going to be pi R2 squared. So the radius 1 is 3 centimeters. Radius 2 is 2 centimeters. And then we'll multiply by the 5 meters per second. So this is 11.25 meters per second. It's faster because the pipe has narrowed down. All right, so now we have enough information to plug in to Bernoulli's equation over here. So the gauge pressure at point 1 is 75 kilopascals. I want to put in 10 to the third for the kilo. Density of water, again, 1,000 kilograms per cubic meter. V1 is 5. V2 we just found out was 11.25. And then Y2 is 2 meters. Okay, I'm getting 4619. I have 2 sig figs, so gauge pressure 2, I'm going to write in kilopascals since they gave us the first gauge pressure in kilopascals. It makes sense that they would both read in kilopascals. So this pressure is 4.6. The pressure is a lot smaller. And the reason why is the kinetic energy is much higher, the potential energy is much higher. But this whole thing must be constant. So if this gets bigger and this gets bigger, this has to get smaller. The pressure in the fluid will be smaller.